Okay. So last time we defined the notion of pivotal structure. Which is isomorphism of monoidal functor between the identity and the double dual functor. And we provided some picture as a reformulation of this notion. And we said that a rigid monoidal category with a pivotal structure is called a pivotal category. So now, the pivotal structure is usually denoted by the letter A. So now let us provide some lemma, some result about the pivotal structure. And most of the proof will be done pictorially. So lemma 0. Ceci, c'est last course, last session for the pictorial definition. So lemma 0. So let A be a pivotal structure. Let A be a pivotal structure, then so you take this isomorphism AX for some object X, and you consider the dual of this isomorphism, and that should be equal to the isomorphism for X star inverse. So we can take inverse, it's an isomorphism. So we want to prove that. So to prove that, to prove lemma 0, we will need two extra lemma. So lemma, we will need the lemma 1 and lemma 2. So what is lemma 1? Lemma 1 is a relation between evaluation co-evaluation map and the dual. So evaluation map for an object X, if you take the dual, that is the co-evaluation of the object X, the dual of X. And similarly, you take the co-evaluation map dual is the evaluation map for X dual. So that is so we can prove that directly using a picture. So the evaluation map of X dual. So pictorially, pictorially. So you consider the evaluation X is of this form. So you have X X star X You do like that, and you have 1. But you can see this just as like that. Fx. Here you have x star tensor x, and here you have 1. And you can also see that just x star tensor x, and we don't draw the 1. So anyway, so here are several ways to draw that. Fx. So if you want to take the dual of that, you take the easiest with one leg and tensor. So you consider you have Fx, and you have that, and you take the dual. So we know that this is 1, so we can just put some dot like that, but we don't need to care about that. This is just 1. And here we have x star tensor x, and then you apply the co-evaluation map here. So what you get here is a dual x star tensor x double star. So this is the dual of the evaluation map. Now, if you draw it, so if you draw the evaluation map like that, you draw the evaluation map like that, but with this one here, what do you get? So you have the evaluation map here. So this corresponds to what you put inside. And then what about this? This should be something like that. So you draw it. Okay. So here this is if you want the box, this is the box. Okay, and here you have x star, x double star. And now you just need to apply one zigzag relation to that. So you apply the zigzag relation here. Zigzag relation, and so you get something like that, and the other part. So x star, x double star, which is exactly the co-evaluation map of x star. So that is really easy. This is really easy. So we get this, and we can get this similarly. So don't need to write the second one is the same. So similarly, co-evaluation x dual is evaluation of x dual. Okay. So that was the first lemma we need. Now, what about the second lemma? We need to prove lemma 0. Okay. So maybe here I should write, because I write a lot of several equivalent picture for that. So I should draw also the picture I use. So this picture. Okay. Okay. So X star X. Okay, so what about lemma? The other lemma we will consider here, lemma 2. So this lemma 2 is it's a pictorial lemma. So consider you have lemma 2 is we want to move the pivotal structure in some picture. So you have the pivotal structure for X star, and you consider it in such picture. So X star, X double star. So the lemma says that this is equal to have the pivotal structure on the other side, but you take the inverse and you replace X star by X, like that. X star, X double star. So the lemma said you can move this on this way, but you have to replace X star by X, and you have to put inverse also. And also, similarly, we can prove for a picture like that. X double star, X star. We can move on the other way. And you have to put X star and the inverse. X. So I recall that this picture is just a way to write something which is a well-defined category in monoidal category, rigid monoidal category, because this part is a co-evaluation map, and then you compose. Here is identity, so it's okay. So how to prove this lemma? So we will prove this lemma using the previous lemma. So by lemma 1. We know the evaluation map of X double star. This evaluation map of X star star. So which is the co-evaluation of X star star, which is evaluation of X double star. So that's okay. If you take double star for evaluation map, you just need to put double star inside. And then we use a pivotal structure. Then by pivotal structure. So pivotal structure. The pivotal structure applied to the evaluation map. So you have the evaluation map double star composed with the pivotal X, and here to compose with the 1, but we don't need to care about that because this is just the identity of So we can forget. This, so pivotal structure tells that this is equal to evaluation of X, and we know that the pivotal structure say that the pivotal structure is monoidal. So the more this is monoidal in that sense. So then what can we say? So let us start from we start from that, and we will prove this is equal to that. So we start from that. We have X star, AX star. Here is X star, X double star. This is equal to, so we will put here an isomorphism and its inverse, composed with its inverse, so that will be identity. So you can, so we will put, so we have AX star. And here we will put some morphism, some isomorphism and its inverse, so that we got the identity. And so we will put this isomorphism AX and AX inverse. So so now we can apply what we wrote. So I will make that better. But I want this to be really in the same level like that. So now, see, so this is equal to the identity of X, of X double star, in fact, to be correct. And this part is equal to the evaluation map of X. Because of what we wrote before. This is so where is it? Yeah, because of that. So so let me check here to be more precise. This is here, it's evaluation is equal to evaluation map of X double star. So you apply, we know that this is equal to evaluation X double star, and then you compose with that. So what you get here, so let me, that you get here like that. This is equal to evaluation of X here. Okay. So I hope it's not confusing. I try to make clear with this picture, with this color, but maybe to put too much color. Yeah. Well, I guess it's okay. So we have evaluation X. So you can replace it. So let me recall. So this is evaluation X double star, which is equal to evaluation X star star. That's okay. Then you apply this one, which corresponds to that. And this is evaluation of X. Okay. So now you can replace it by its by the picture of fx. Easy. So you have ax inverse here, x double star, and you have the picture of evaluation x, and then you continue. X star. So here fx, and this is what we wanted to prove. In fact, we were able to move this on the other side. So the trick was to use this identity and to write the identity like that, and then just to apply what we already proved in the lemma 1. Okay, and the pivotal structure. So same for the other. For the other picture. So idem for the other. By other, I mean this one, this equality. You do the same. So you get what we wanted to prove, lemma 2. So now we can apply that to prove lemma 0, to prove this equality. Okay, so now let us prove this equality. Okay, so proof. Now we can prove lemma 0. Alors, lemma 0. So you start from ax. You start from ax, and you take the dual of this morphism. So ax dual, it's equal to, you start from ax, and you take the dual. But now we know by lemma 2 that we can move the ax in some other branch. So we will move the ax, we will move ax here. So by applying this lemma 2, we move this. So we move on the other branch like that, on the other leg. So you take inverse on the x dual, and so we are in the other leg. Now we can just apply the zigzag relation. We can apply the zigzag relation here. So by zigzag, what you get is just what you wanted to prove. So you get just this red line corresponding to the application of the zigzag and ax star inverse. So it is precisely x star inverse. What you wanted to prove. So we prove that double star. So I forgot a double star somewhere. What is? So I have a problem. Wait. Ax. Yeah. So you move. You put the star. Then you have to put the star here, but the inverse also. Okay, so this is what we get. So it's okay. It's okay, so we proved this lemma 0. So now we can prove you can apply now. We can apply lemma 0 as follow. We get another lemma we will need. So if you apply the double star for the pivotal structure isomorphism, then you can, it's the same that take the double star of the object. So it looks like what we get here. In fact, we get something similar here. But here you just have to apply the lemma 0 2 times. So and with a slight detail. So so proof AX double star is AX star star. So here you apply lemma 0. So this is AX star inverse star. And the problem here is we need to commute this inverse and this star. So so we will prove that we can do this commutation. So we will prove here. So it's quite straightforward, but we have some place here, some room. Okay. So how to commute commutation of you have inverse and you can commute the two. So you start from the identity. The identity by zigzag relation, you can write like that. And then this is equal to, so we will consider, we will consider an object y. We will consider an object, y equal x star. We will consider, we'll write the letter y. So here, as before, you can just apply a y and its inverse. Okay. So this, you can again apply some zigzag relation. So you get like that, a y inverse a y. And here you have the zigzag relation. And then like that. But this part is now the dual. You apply the dual of the morphism. So this is equal to like that. So you have the dual. So a y inverse dual in this box, and then a y like that. So we started from the identity, and we get that this is a composition of that and that. So that should be, the second one should be the inverse. So a y. So I forgot a star somewhere. Wait. Yeah. You have, this is also the star here, because it's also the, you have the dual of that and the dual of that. It's the composition of the two dual morphisms. So you need to put the dual and here and here. Okay. So you have a y dual composed with a y inverse dual equal to the identity. So everything is isomorphism. So we have the commutation we expected. AY dual inverse equal AY inverse dual. So you apply so you apply that with a y equal x star. So you get a x star star inverse. And now you apply again lemma 0. And you get a so lemma 0. What is lemma 0? Ax. You apply lemma 0 with x star. We have ax double star inverse and inverse. So it is ax double star. And this is what we wanted to prove. So we get, so it's almost the composition of lemma 2 times lemma 0, but we have some technical details here. We need to commute star and inverse. So these two functors, taking the star and taking the inverse, can be commuted because of this proof. Okay, at least in this case. In fact, yeah. So this proof is not specific to the pivotal structure. In fact, you can take any isomorphism. Let me check. So if you take any isomorphism, so A, yeah, it works for any isomorphism. So you take, how to say, B. So B equal AY isomorphism. You can take B inverse. B inverse B. So here it's B. So here with y equal x star and b equal a. And here we can just take So for any isomorphism B, like that. So we have something. So that should be a I should write that as a lemma, but anyway, quite straightforward also. So we have this result. Okay. In general, for any isomorphism, you can commute inverse and dual. Okay, so what time is it? Almost pause. Okay, so we prove we prove lemma 0. And we applied to prove this lemma here. So now so let us provide some so we define what is a pivotal structure, a pivotal rigid monoidal category. We provide some easy properties. So now what about some easy example? Example of pivotal category. In fact, every example we already mentioned all have a pivotal structure. Vec G, rep G are pivotal. They are pivotal. So as have pivotal structure like that. Just coming from the usual natural isomorphism from at the vector space level. You take the dual as a vector space, so the space of form, and the double dual, so the dual of the dual. And this is a pivotal structure on the usual example. It's okay. So now, what time is it? So 5 minutes before the pause. So we will talk about dimension now. Categorical dimension. So we already, as I said, in fact, in the introduction part of this new chapter, of this new section, I said that we already defined the Frobenius-Perron dimension, but there exists another dimension, a categorical dimension, we will define now. And I said that a pseudo-unitary category is when the Frobenius-Perron dimension is equal to the categorical dimension. And I said that there is a notion of unitary category, and unitary implies pseudo-unitary. A unitary category, you meet that in physics and in subfactor theory, coming from analysis and fundamental algebra, etc. So what is a categorical dimension? here that will be called just dimension. So the dimension of an object X in the category so we consider a category a rigid monoidal category. So let me draw this before. So let A be a pivotal structure on a rigid monoidal category. Category C. So what is the dimension of an object? Here. So the dimension, in fact, is given with respect to the pivotal structure. So there is no absolute notion of dimension except the Frobenius parent dimension, but here for a categorical dimension, we need with respect to some pivotal structure. In fact, you can have several with respect to A is so dimension with respect to A of the object is exactly the left trace of the pivotal structure isomorphism on X. Now, this is an object, this is a morphism from 1 to 1. So in a tensor category, this is a scalar in a tensor category. In particular, in a fusion category also, over a field K, dim A of X is a scalar. So it's an element of. Okay. So we will prove, after the pause, we will prove the following lemma. Dimension of an object V with respect to A is equal to the dimension of V double dual. So proof. So this is a pause. Yeah. Take the pause now. So, so proof of that. So we will use, we will obviously use lemma 3, in fact, and some picture. So, so the dimension of V double star according to A is, by definition, the left trace of A V double star, but we know that lemma 3 that A V double star is precisely A V star like that. So now you can write A now A V double star is equal to, so you take the the dual, and again the dual. So the left trace of AV double star is like that. So you have AV tac, tac, and then you take the trace, you apply the trace formula. So you do like that, you close like that for the trace. So you do like that. So let me draw something better. So you do like that, and then like that. Okay, you do that, but by zigzag relation. So you apply zigzag relation here. So you may apply zigzag relation several times. So zigzag relation. So you apply the zigzag relation one time here. So you get zigzag. So wait, no, not here. Where should I apply the zigzag relation? Tac. Wait. Just here. One. So replace that by just a single straight line, and then you have AV. So you have this line, and then so it should be like that. Okay, and you should apply zigzag relation again. So it's equal to that AV. And here you apply the zigzag relation to the zigzag again. So here, click. Yeah, so you apply zigzag here, like that. Here. So you get this part. Zigzag. Okay, so you get what you want. You get, so this is equal. This last is equal to the left trace of AV. So this is equal to the dimension, by definition, dimension A of V. Okay. Okay. So it's okay. write here. So it's equal to of A, dimension A, V, what we wanted to prove. Okay. Okay. So you don't know where to put it, this to be understandable. Otherwise, you say this one. So this is, you can go directly, but it's not true. You have to, so I'm a bit confused. So this is equal to left trace of AB is equal to dimension A of V, which is what we wanted to prove. Okay. It's a bit better than that. Okay. So maybe I should put everything on the left. That would be even better. I will not take too much time for that. I want to do that. This is zigzag. Just that. Here. Oh, that don't move the zigzag. Strange. Okay. So this one was applied to here. And then we applied to here. Okay. So this is equal to A. Okay, sorry about that. Zigzag. Okay. Okay, so now, so now I need to mention something about the pivotal structure and direct sum. So I was a bit confused, in fact, in the book, because the pivotal structure is defined for a rigid monoidal category. So a priori, the category don't need to be abelian. But we will need later, we need something like that. So we already know that, but we need the additive equivalent of that. And in a monoidal category, we don't have that direct sum. We need abelian category, but we need that. So I don't know if it is an exercise that you can prove that. I don't know if it is an exercise or an assumption. It's in. So yeah, so I will put it as an exercise because it's, but maybe it should be assumed also. Oh, assumption. Exercise. So let C be a tensor category. So it's a modular category with some additional structure like it's abelian. So you have the direct sum. Let A be a pivotal structure. Then AX direct sum Y is equal to AX direct sum AY. So the question is that can you prove that for any tensor category, or should you assume the pivotal structure to be to have this abelian structure? So it's additive. In other words, the pivotal structure is additive. So the problem I got by reading the book this morning is that can we prove that the pivotal structure is additive, or should we assume it to be additive? In any case, we will need that. So we will use that. So okay. So proposition. Yeah. So the next proposition is very important. He's saying that the dimension, as defined before, provide a character on the Grothendieck ring. It's a character on the Grothendieck ring. And in fact, you can have several characters in the Grothendieck ring, and you can have also several dimensions. I guess the converse is true. In fact, any character on the Grothendieck ring provides yeah, I don't know. Anyway, so the converse may be true or not. Proposition. So let C be a tensor category. So let's see a tensor category. And as before, and let A be pivotal structure. Then so this map on the Grothendieck ring, from the Grothendieck ring to to the field, is a character. By character, I mean the character. It's a morphism, homomorphism of ring. Is a character of the Grothendieck ring. Grothendieck ring, GR. So character, I mean homomorphism, ring homomorphism. So ring homomorphism. So this is in K, the field. Okay, So how to prove that? So proof. So we already mentioned in some previous proposition that the trace is additive on the exact sequence. So we already know that. We stated that with our proof, but we put a hint. So is additive on exact sequence. So we say it's additive on exact sequence because we are here, we don't assume to be semi-simple. Otherwise, you just say it's additive on the direct sum. But because the book provides something more general than semi-simple, that make everything a bit more complicated, but okay. So the dimension is well defined on the Grothendieck ring, because the Grothendieck ring you define on the simple object, and then you make some sum according to how the Jordan-Holder decomposition of the object. So because the left trace is additive on exact sequence, you can have so it's well defined. Again, on the semi-simple case, this is trivial, but on the non-semi-simple case, you need to be careful a bit, which then is well defined. Is a well-defined linear map from the Grothendieck ring to the field. So next, what about, so it's okay for the, it's a linear map, so it's okay for the addition structure. But what about the multiplication structure? And the multiplication structure is it's okay also. So about multiplication. So as I said, ring homomorphism here. This means that it's okay for it deal with correctly with addition and multiplication. So linear map is it's okay for addition. Now, what about multiplication? Multiplication. So we already know when we talk about Grothendieck ring, we already know that the tensor product of the class in the Grothendieck ring is the product of the two classes. So we know that on one hand, but on the other hand, dimension A of X tensor Y is the left trace of X, but by the pivotal structure. We can, by pivotal structure, this, you can split that. So trace left AX tensor AY. And then, so we mentioned in some previous proposition last time that we can also, the trace of the tensor product is the tensor product of the trace here. So it applies. So I guess that was proved for we prove that for any morphism, yeah. So it's not true for any morphism, but here the morphism, we prove that when these morphisms are homomorphism from V to V double star, from W to W double star. So it's a morphism which are the same structure as it's an isomorphism between X and X double star. So this is always true. You have this multiplicativity in general. So you don't. What I mean, you don't need to apply pivotal here. This is true for any isomorphism like that between X and X double star, Y and Y double star. We proved that in some previous proposition. Okay. So that's okay. And then this is equal to the product of the dimension. This is dimension A of X times dimension A of Y. Okay. And then it's a homomorphism of ring, so it should also preserve the unit. And finally, the dimension of the unit object. So trace left of A1, but A1 is just the identity of 1. So yeah. So if you want to write the details, so this is equal to. So I will write the details in green because this is completely straightforward. So this is equal to evaluation map of 1 composed co-evaluation map of 1, which is identity 1 in as an object of and C of 1. This is what we call 1 in because this is equal to that. Is equal to 1 in the field. And C. It's not clear. Okay. So the dimension A of 1 equal 1. So equal 1. Okay. So it's okay. It's a ring homomorphism. It's a character. Okay. That's good. So in fact, that's really, really interesting because if you want to have an idea of what should be the dimension on some tensor category, you just need to choose, to find one character. So when you have a fusion, a Grothendieck ring or a fusion ring, it's very easy to classify the character, at least if the fusion ring is commutative. You can compute what is called a character table, and this is very easy to do. And then this dimension will be one line given by one line or one column in this character table. And this character table generalizes the notion of character table for a group. Finite group. Okay. So next result will be about. So the next result is saying that the dimension of an object in a finite pivotal tensor category should be an algebraic integer. An algebraic integer. But this is exactly what I just said, in fact. It should be a value in some character table, and we know that in some the value of character table are algebraic integer. So dimension of object in a pivotal finite tensor category are algebraic integer. So proof, so we will do it very brief. So by finiteness, the Grothendieck ring is a finitely generated Z module. Finitely generated Z module. But for a finitely generated Z module, it's well known that the character table are algebraic integers. So I don't want to go into the details. This is well known in algebra theory. But for such a ring, a character has values in algebraic integer. So this is well known. Well known. Okay. Well known. Okay. Okay, what time is it? So it remains 15 minutes. So now let us talk about another important notion called sphericality. So this is related to the notion of pivotality. Definition. So a pivotal structure A. So pivotal structure A on a tensor category C is called spherical if the dimension of V with respect to A is the same as the dimension of its dual for all V in C. So we proved that in general, for a pivotal structure, the dimension of V is equal to the dimension of its double dual. But we prove that here. But it's not true in general that it's equal to the dimension of its dual, just dual. This is the sphericality. Okay. So when I say it's not true in general, in fact, there are some conjectures saying that every tensor category has a spherical structure. So maybe maybe it's true, maybe it's open for the semi-simple case, whether they always have the spherical structure, but maybe for non-semi-simple case, we will mention some counterexample. We will talk about that later. So then a tensor category is spherical if it has a spherical structure. If it has a spherical structure. Okay. So, as I said before, when you want to recognize a spherical structure, you consider the character table of the Grothendieck ring, and you consider the line or the column where the dimensions are real, because this, at least in the complex field, that should be the complex conjugate of this. So if they are equal, then this is equal to its complex conjugate, so it's real. So you should consider the line or the column in the character table where everything is real to have a spherical structure. So it's a good way to find the value of that. You use a character table and you get, or to prove something about that. For a given fusion Grothendieck ring, you consider a character table, and you consider all the real line or real column. And if you can prove that for every real line, real column, then you can prove that for any spherical structure. Okay, so next. So so we can remark. So in fact, because the dimension with respect to a pivotal structure is additive according to exact sequence, we only need to define that, or to consider, we only need to check that to be spherical. We only need to check that for the simple object. If it is true for simple object, then it is true. Then this equality for all objects is trivial for semi-simple, but it's also true for non-semi-simple, because the dimension is exact, is additive on exact sequence. So because dim A is additive on exact sequence, we only need to consider the simple in above definition. Okay. So the next remark will be a bit longer, and in fact, the next remark will lead us to a theorem about spherical structure. So the next remark is the following: is saying that in fact, in the literature, you meet some alternative equivalent definition for spherical, and we will prove later that this alternative definition is equivalent. So in the literature, spherical can alternatively be defined by, and we will prove it is equivalent. We will prove that it is equivalent. So defined by the following. So as follow, for all x, all object x, and for all morphism from x to x, then trace alpha is equal to the trace of alpha star where trace of alpha is defined as the left trace of AX composed with alpha. And same for the other. So you define a notion of trace for morphism. Yeah, a morphism from x to x, because we already know a notion of trace for morphism from x to x double star. For example, using a pivotal structure, but we don't have a notion of trace for a morphism from x to x. So you can use that according to some pivotal structure. So you should write according to some pivotal structure. Maybe I can write it first. So according to the pivotal structure A, like that. But we will not write A later. In fact, also for the dimension, sometimes we will forget to write A. We will not write A. If there is no confusion possible, we don't write A. Because we fix the pivotal structure at the beginning. Okay. So this equality is how we define. You can find the definition of spherical in general in the literature. So why this is equivalent to the previous definition? So why? Why the two definitions are equivalent? So the answer is the following. Answer. So the first. So first, if you prove this way. So you start from this definition, and you want to recover the other definition. This is easy. You just need to take alpha equal the identity of x. You take alpha equals the identity of x, and then what you get here is just dimension of x. And what you get here is just dimension of x star. So this is exactly the definition of spherical as given previously. So this way is easy. So the other way is a bit more complicated. If I have time, I will just reformulate the other way. And that will be proved don't have too much time. What about the other way? So we will see that later. I have no time to. I cannot. So we will. So we will see that later. We will. So next time. We will show that trace alpha equal to trace alpha star. This is equivalent to left trace of AX compose alpha equal to the right trace of alpha compose AX. So we will show that, and we will prove the last equality. Equality as a new theorem. So next time we will show this equality, and then we will show this equivalence, and then we will prove this equality. This will be a theorem which will need this theorem will need several slides to prove. In fact, it's not at all trivial. So we'll see that next time. So see you next time. See. Next time. Okay, so we will stop here. We'll stop here.